Okay, let's jump right in. We're looking at a paper called Mimic Video, Video Action Models for Generalizable Robot Control Beyond VLAs.
And this one is really interesting because it's not just a small step forward. It's proposing a pretty fundamental shift away from how we've been thinking about these models.
Moving away from the language-centric approach.
Exactly. So the core problem they're tackling is this scalability bottleneck that we're seeing with vision language action models, or VLAs, things like RT2.
Right.
These models are great, but they're pre-trained on static images and text. And that data, it just doesn't have any explicit information about physics or causality, how things actually move over time.
So the whole job of learning physics, how an object is going to react when you push it, that all falls in the fine-tuning phase.
Which uses that super expensive, super scarce, expert teleoperated robot data.
And that's the bottleneck.
That is the bottleneck. So the solution here is Mimic Video, which they call a video action model, a VAM.
And the idea is to ground the policy in internet-scale video models from the start. Because video inherently encodes how things are done, the dynamics are already there.
Precisely. And for you listening, here's the key takeaway. This change in approach, this decoupling, it leads to state-of-the-art results with way better data efficiency.
And when you say way better, we are talking about 10 times greater sample efficiency.
10 times. You need a tenth of the robot data. And on top of that, it converges twice as fast compared to the VLA architectures.
That's a massive deal. It really changes the economics of training these things.
So let's unpack that VLA bottleneck a little more, because models like OpenVLA have been genuinely revolutionary.
Absolutely. The semantic understanding they get from those huge image text data sets is incredible for generalizing to new instructions or objects.
That semantic transfer is key, no doubt. But the whole thing starts to fall apart when the task requires a really nuanced understanding of physics.
Like, how much force do I need to slide the specific box? Or how does liquid behave when I pour it?
Exactly. A static picture and a text label. That just can't tell you the temporal sequence, the cause and effect of a physical action.
So when a VLA hears stack the blocks, it understands the concept, but it's basically learning Newtonian physics from scratch, just from those few hours of robot data.
And that's the sustainability problem right there.
Yeah.
You can't scale that. The VM philosophy says, let's not do that. Let's start with a modality that already understands physics.
Let's start with video.
Let's start with video.
Yeah.
The internet is just this massive library of how-to guides. It shows object movement, deformation, reactions. It's all there.
It's really the difference between studying a dictionary versus watching an instruction video.
That's a great analogy.
The dictionary gives you the name of the object, the verb, but the video shows you the how, the full physical process from start to finish. The dynamics are just baked right in.
And the entire Mimic Video architecture is designed to exploit that baked-in knowledge.
Okay, so let's get into that architecture, because this is where the really clever stuff happens. It's a decoupled system built on something called conditional flow matching, or CFM. For listeners who are maybe more used to standard diffusion models, what's the quick rundown on CFM? Why use it here?
Right. So conditional flow matching is a really efficient way to train generative models. Instead of taking hundreds of slow steps to go from noise to data, like in classic diffusion, CFM learns a direct deterministic path, or a flow.
So it's much faster.
Much faster to train and much faster to sample from, which is obviously critical if you want to use it for real-time robot control.
And they use this framework to build a two-component system where they separate the kind of big picture thinking from the low-level execution.
That's exactly. Yeah. So component one is the video model. They use Cosmos Predict 2, which is a big 2 billion parameter latent diffusion transformer.
Okay.
And the crucial part is that this model is mostly frozen during the action training. Its only job is to look at the current camera feed and language command and then generate a visual plan.
A prediction of what the future should look like.
A prediction, yeah, but in a really compact latent space. So it handles all the hard parts, the multimodality, the long-term planning, and it offloads it all to this giant pre-trained backbone.
Which then simplifies everything for the second component.
The action decoder.
Yep.
And this is a much more lightweight model, also trained with flow matching. It basically functions as an inverse dynamics model or an IDM.
An IDM. So it looks at the desired outcome from the video model and figures out the exact motor commands to make it happen.
That's it. It's not looking at raw pixels or language anymore. It's only conditioned on that clean, high-level visual plan.
And the efficiency gain from that decoupling must be huge.
It's enormous. Because the giant video model is frozen, you're not spending expensive robot data to retrain it. And because the little action decoder doesn't have to worry about predicting complex video.
The video model already did that.
Right. It can just focus all of its capacity on the much simpler problem of inverse dynamics that makes the whole system incredibly data efficient.
And the training process reflects that split.
It does. It's two distinct phases. First, you just fine-tune the video backbone a little using LoRa just to align it with the visuals of your specific robot.
So you're not retraining the whole 2 billion parameters.
Oh, Dad, no. Just adapting it. Then, phase 2, you freeze that video backbone completely, and you train the action decoder from scratch, conditioned on the video model's outputs. It's a really clean separation.
So to prove that this performance boost really comes from using video as the input and not just, a better model design, they ran a really important baseline comparison.
Yeah, this is key. They built what they call a Pi 0.5 style baseline. It uses a VLM, specifically palette gemma, but the action decoder is identical to the one in Mimic Video.
So you're controlling for everything except the conditioning signal. It's video latents versus image text latents, a true head-to-head.
Exactly. And the most revealing part of this is what they call the Oracle case study.
Ah, yeah, this was fascinating.
So here, instead of feeding the action decoder the predicted future from the video model, they feed it the ground truth future video latents. The Oracle input.
The perfect answer.
The perfect answer. And when they do that, the action decoder achieves near perfect success rates, almost 100%.
Wow. So what does that actually mean?
It's a huge insight. It basically implies that the hardest part of robot control isn't the low-level action execution. It's not the inverse dynamics.
It's the high-level visual prediction. It's the planning.
Exactly. If you can give the robot a perfect blueprint of the future, figuring out the actions to get there is almost trivial.
So the performance of your entire policy just scales directly with the quality of your video generation model. If you can see the future, you can make it happen.
That's the paradigm shift, and you see it immediately in the numbers. The VAM action decoder hits the VLM decoder's peak performance using only 10% of the training data.
An order of magnitude improvement?
And they pushed it even further. With just one demonstration per task, which is a 98% data reduction, Mimic Video still got a 77% success rate. It's just wildly efficient.
And it's faster, too. Converges twice as fast to a better final result. I mean, the advantage for anyone trying to deploy this stuff in the real world is undeniable.
Okay, so this brings us to what might be the most counterintuitive finding in the whole paper.
And maybe the most practical one.
Possibly, yeah. It's about the role of noise, controlled by this parameter, tau-v.
Right. So TAV is a number between 0 and 1 that you set at inference time. It controls how much you denoise the future video plan before you give it to the action decoder.
And your first instinct, my first instinct, everyone's instinct, is that you want zero noise, right? A TAV of 0. You want the sharpest, clearest, highest fidelity prediction of the future possible.
Give the robot the best possible blueprint.
Of course. But the results show the complete opposite. On the simpler bridge benchmark, the best performance comes from the highest noise level, a TAV of 1, or somewhere in the middle, around 0.4. The perfectly clean prediction is actually worse.
That feels completely wrong. Why would giving the robot a fuzzy, noisy plan lead to better execution?
Well, there are two main reasons. The first is about distribution mismatch. So that perfectly denoised prediction, the TAV equals 0, 1, it might look great to our eyes, but it could have subtle artifacts or just be slightly weird compared to the real-world video that the action decoder was trained on.
Ah, so it's like the decoder was trained on real photographs and you're showing it this perfect but slightly unnatural CGI render. It gets confused.
That's a perfect way to put it. So leaving some noise in, especially up at TAV equals 1, it acts like a kind of data augmentation. It forces the policy to be more robust and not overfit to tiny, spurious details in the generative plan.
Okay, that makes sense. But what about the second reason, the information content?
Right. This is also really interesting. As you get closer and closer to a perfect prediction, to TAV equals 0, the model's internal states, the hidden representations, actually become less informative about the transformation needed to get there.
I think I follow. The critical information for the action decoder isn't just the final picture, it's the path to get to that final picture.
Precisely. The earlier, noisier states, like around that TAV of 0.4, they contain richer information about the scene dynamics, about what needs to change. That's a much more useful signal for the inverse dynamics model than just a static final frame.
And the practical payoff here is huge.
It's massive. Because operating a TOV equals 1, the noisiest setting, requires only a single forward pass of that big, expensive video model.
So you get the fastest possible inference speed.
And the highest average performance. It's the best of both worlds. A huge win for real-time control. So the paper really backs all this up with some strong experiments across 3 totally different robots, which is great for showing how generalizable this video prior is.
Okay, so first up, they used the simpler bridge benchmark with a Widow X robot, right? Which is all about testing generalization to new objects and scenes.
Yep. And Mimic Video got the strongest average success rate across all the generalization tasks. It just confirms that the video knowledge helps the robot adapt to things it hasn't seen before.
And then they moved on to something harder, the Libero benchmark.
Much harder. This uses a Panda robot for these really complex, multi-stage manipulation tasks. It tests things like task compositionality.
And what's really impressive here is that Mimic Video, even trained completely from scratch, beat most of the other big state-of-the-art models that had been fine-tuned.
Yeah, hitting a 93.9% average success rate there is. That's a phenomenal result. It shows the VAM architecture can learn these complex structured skills really, really quickly.
But I think the validation that should really get people's attention, especially if you're working on real-world systems, is the dexterous bimanual robot.
Oh, absolutely. The Mimic system. This is a real test. You've got these high-dimensional, contact-rich tasks like sorting packages or stowing tape.
And lots of occlusion. The hands are always getting in the way of the camera.
A huge amount of occlusion. So much so that the baseline models, they needed multiple cameras, including wrist cameras, just to be able to see what was going on.
But Mimic Video didn't.
It didn't. And this is the kicker. Mimic Video, conditioned on just a single workspace camera view, still massively outperformed the multi-view baselines.
What were the numbers on that?
On the handover task, it hit 93% success. The competitive multi-view baseline was stuck down at 74%.
That is a massive gap.
It's enormous.
Yeah.
And what it proves is that the generative video prior, its ability to predict, is effectively bridging that visual uncertainty. The model is using its knowledge of physics to kind of hallucinate or fill in the blanks for what it can't see.
And it's doing this from what, just a couple of hours of data?
Yeah, we're talking about 1.5 to 2 hours of demonstration data per task. It's an incredibly small amount of data to learn such robust policies.
So, to wrap up this deep dive, Mimic Video really puts forward this new video action model paradigm. By using these dynamics priors from big video models, it seems to crack the data efficiency problem in robotics.
It really does. It delivers these order of magnitude gains in sample efficiency, in convergence speed, and in robustness, especially when things get messy and occluded in the real world.
The path forward seems to be video foundation models, not static language models.
That seems to be the most promising direction, yes. But the authors are, very clear about the limitations that are still there.
Right. They mention that it's still a single view system, and the next step is obviously natively multi-view video models for better spatial awareness. And the ultimate goal is, a single, unified, cross-robot model.
Exactly. Which brings us back to that provocative thought from the Oracle study.
Right.
If policy performance is almost entirely limited by the quality of your visual prediction, not by your action decoder.
If perfect planning makes action easy,
then what does that mean for the future of robotics research? Does it mean we should be investing less time and compute on refining these complex action policies and more on just building bigger, better, longer horizon video generation models? What does that shift in focus mean for how you, listening, should be allocating resources in your own work?